What's up, Prof 301 crew? Let's start off talking about introductory concepts in kinesiology. Let's get it popping. So, what is kinesiology? What does this term mean here? So, kinesio meaning movement, ology meaning study of. So, essentially, kinesiology is the study of human movement. And essentially, kinesiology can refer to a lot of different things and areas there. Some of these areas include the following list there: biomechanics, exercise physiology, motor behavior, psychology of sport, and sociology of sport there. In this class here, though, we're going to mainly focus on biomechanics, exercise physiology, and motor behavior. So when we're talking about movement there, typically there's two types of movements that we typically look at. One would be static and the other would be dynamic. Static means either staying still or moving at a constant velocity. A couple of examples this might be for staying still would be holding a front plank. Holding a front plank would be an example of a static movement. Versus jogging and maintaining a 10 mile per hour pace there, since we're maintaining the same speed there, jogging at that same speed would be considered a static movement. And I know it doesn't seem like it because jogging you're moving, but because you're maintaining that same pace there, that's why it'd be considered a static movement. On the other hand, we've got dynamic movements. And dynamic movements have some sort of acceleration that is going on. Okay? Acceleration could be something that's speeding up. Okay? Maybe it's something that's slowing down. Sometimes you might hear people say deceleration, and correct, that deceleration would mean slowing down there, but think of slowing down as a kind of acceleration there. So speeding up, slowing down, or changing directions. So if I'm starting going to the right and then all of a sudden I change directions to go to the left there, that would be considered a dynamic movement. So a couple examples of this is the first 30 meters in a 100-meter dash. So within that first 30 meters in a 100-meter dash, typically people are going to be accelerating or speeding up there. So because their speeds are changing, that's why it's considered a dynamic movement. Another example might be jumping, because jumping means incorporates some sort of change of direction. So for example, I'll jump into the air, and as I jump into the air there, I'm going up. Okay? But then gravity will pull me back down, so I change directions, okay? And therefore jumping would be considered a dynamic movement. So when we're talking about movements, we will often kind of base these our scientific understanding of these movements in Newton's 3 different laws. And you may have taken some classes prior to this where you've dealt with Newton's laws there. So in this chapter here, we're going to be talking about Newton's 3 different laws. The first of Newton's laws is the law of inertia, okay, which says basically if something's not moving, it's going to have a tendency to not move. Or if an object is moving, it's going to continue moving at that same speed in that same direction unless some sort of force acts on it that's outside of it. Okay? And we'll talk a little bit more as we move on throughout this course there on kind of what Newton's law entails. So when we looked at that definition there are some terms that we will need to define, and we'll see these used over and over again. They are inertia, mass, and weight. Okay, so inertia is either a person's resistance to changes in its motion or an object's resistance to changes in its motion. So essentially Newton's first law. So if we say inertia, think back to Newton's first law, meaning if I'm staying still, I have a tendency to stay still, or if I'm moving in one direction, I'll continue to move in that one direction unless an outside force acts upon myself or a particular object there. Now, when we have objects or ourselves as people there, okay, we have a certain amount of mass. Okay, so think of mass as the total amount of molecules that we have in our body, essentially the total amount of matter that makes up an object there. Now understand, mass never changes. We could be wherever we possibly could in the world, or maybe on some other worlds, such as the moon, maybe Mercury, Venus, Uranus, Neptune, Pluto. We could be on any other planet, and the total amount of matter that makes us up, okay, total amount of mass, that will never change. Typically in the research there, we typically measure mass, especially in terms of human movement, in terms of kilograms, abbreviated with kg. Now, mass kind of is similar to weight. Okay? Now, weight is a little different than mass, though, because weight is the measure of the force of gravity acting on that person or that object's mass there. Okay? And because the force of gravity is different depending on which planet we're on, for example, Earth has a lot more gravity than the moon. Okay? That will change your weight based off of which planet you're on. So if I'm on the moon, since the moon is a lot smaller, less massive, okay, it's got a less pull of gravity on us. So therefore, I will weigh less on the moon, but I will be way heavier on Earth. Contrary to that, though, my mass on the moon will be the same as my mass on Earth there. So understand, a lot of times we'll use mass and weight interchangeably, but they aren't technically the same. So let's talk about Newton's second law. So Newton's second law is the law of acceleration. Okay. So basically what they're saying is that if there is an external force that is exerted on an object or a person, okay, that person or object will accelerate in the direction of that force there. Okay? And the acceleration will be directly proportional to the force and inversely proportional to its mass. Okay? If, for all you math nerds out there, okay, if we were to try to calculate what force is, okay, sum of forces, so this funky E symbol is sum of, so if sum add up all the forces, okay, that equals mass times acceleration there. Okay. So for a force to exist, there must be a mass and there must be some sort of acceleration. Okay. Now, assuming there is a mass on an object, which there should be since we exist there, okay, if an object is not accelerating, okay, we might think that there might not be a force that is being applied to that particular object. Okay. However, let's think about that there, and we'll kind of come back to this point in the next couple slides there. Okay. But the big idea from this section here is the law of acceleration says that the sum of all our forces equals the mass times the acceleration. So what is force here? We've been using that term force. Okay, force is a push or a pull. Okay? Very simply, push or a pull. So for example, I can push someone. Okay, let's say my little brother's getting on my nerves there, and I want to push him to get him out of my face there. Okay, as I push on my brother there, I'm producing force on my brother. Likewise, okay, we can produce force by pulling things. Okay, for example, if you're playing tug of war there, pulling on that rope creates force there. Okay, and so essentially, force is something that causes or tends to cause a change in the motion or shape of an object or a body. Okay, so essentially, force oftentimes will change the shape of a person or object there, okay, or will change that person or object's motion or movement. Essentially, forces accelerate objects. Okay, they can start moving an object, they can stop an object, speed up, slow down, or even change directions. Typically in the literature, if we're trying to measure force, we measure it in newtons, symbolized by the letter N there. Okay, and so essentially, what a 1 newton is the force required to accelerate 1 kilogram of mass, a total of 1 meters per second squared of acceleration there. Okay? And so if you wanted to do some sort of calculations, okay, these would be kind of examples of how you would do that there. Again, in our class here, the vast majority of stuff we're doing is not going to be mainly focused on math stuff, but for some people who are more mathematically inclined, it might give you a better idea of where all these terms, how they deal with in terms of mathematics. Now, force is a vector quantity. Okay? And what a vector is that it means that force has some sort of magnitude, okay, or the how large or small that force is, and then direction. So which way is that force moving there? Okay. We'll talk about some terms in this class here that are considered scalar quantities. And scalar quantities only have magnitude. Essentially, all we're worried about is how large or small that quantity is. But force there, when we have forces, we worry both about how large or small it is, as well as the direction that that force is moving. With forces, there are internal and external forces, and we'll talk about those in the next couple slides. So kind of going back to, again, what we were talking about before, if there is to be some sort of acceleration, going to Newton's second law there must be a net force there. Okay. So if the net force is 0, that means acceleration must be 0. So it makes us think here. If we're not accelerating, are we actually applying any force? Okay, because if I'm walking or running at a constant speed, it sure definitely feels like I'm applying force. If it didn't feel like I was applying force, I could walk or run forever, but obviously I'm going to get tired. So therefore, I'm producing force there, okay, to move, even though I'm moving at a constant speed. On a similar vein there, if I am holding a front plank position, okay, I'm not moving at all, so there's no acceleration going on, okay? So therefore, you would think that there's no force happening. But again, I can't hold a front plank forever. My ab muscles will eventually give out and I will collapse there. So I'm definitely producing force when I'm holding that plank position. Okay? So therefore, just because no acceleration is happening does not necessarily mean that no force is occurring. And what we need to take from this is that if there's some opposing force that is identical in magnitude, means how much force is producing, okay? Opposing force to the force that we are producing, the forces will cancel each other out. Okay? So therefore, the sum of all the forces acting on an object are referred to as the net force. So if there is no acceleration happening, but there are forces that are at play. And again, example there, if I'm holding a front plank position, I'm definitely creating force with my ab muscles there. Okay. So if there's no acceleration but forces are occurring, then we know that the net force is 0. Going back to a previous slide there, okay, we talked about we introduced, I guess, that there was two kind of category of forces. There are internal and external forces. So what internal forces are forces that are acting within a particular object, particular person, or a particular system. Okay. Pulling forces, pulling internal forces are called tensile forces. Tensile, think of the word tension. Okay. So pulling forces create tension. And oftentimes when we're thinking about the human body there, muscles are within the human body there, and muscles pull on tendons, which in turn pull on bones. So muscles and tendons create pulling forces on bones there. Pushing for internal forces are compressive forces that happen within the human body, for example. Okay. An example of this would be your quadriceps and patellar tendon, essentially your big thigh muscle there, okay, and the tendon there that attaches to your kneecap. Okay. Essentially, it pulls on your patella or your kneecap, okay, and that in turn pushes your kneecap actually into your knee joint, causing compression. That's one example of a compressive force there. So, internal forces, okay, understand that internal forces can create movement around the center of mass of an object or a body. To keep things simple for now, center of mass essentially is the middle point of your body. We'll talk about that a little bit more later on in this course here. But internal forces can create movement around that center of mass. However, by themselves there, okay, just left alone, imagine you kind of just like being in space there, okay? If just left by itself, these internal forces cannot produce any change in the movement of the center of mass. So if I was floating in space and I squeezed my quadricep muscles, okay, or I've moved my arms and legs there, okay, creating movement in my body, yes, I would be moving around my center of mass there, but that wouldn't change the direction in which my center of mass is moving. So if I was kind of just floating through space, I can move my arms and legs every which way, but I would continue moving that same direction even though I was flailing my arms and legs. Okay. Essentially, internal forces need some sort of external object to push off of or pull off of in order to change the movement of our center of mass. Again, don't worry about that for now. We'll talk about that later on in this course. In terms of internal forces in the literature there, they mainly focus on biomechanics in terms of injury. Okay? So typically we look at internal forces if we're looking at something that's injury causing. Okay? Our focus this semester is predominantly going to be on movement. So yes, injury is a big thing, but our focus is more on movement. External forces will be play a bigger role in our discussion here in this course. Okay, so unlike internal forces, which are forces created within a person or an object there, external forces are forces that act on a person or an object or a system, okay, that come from the surrounding environment. So coming from the external. Okay. So only external forces can actually move a system or move your center of gravity or your center of mass there. Okay. That only external forces can cause that. Okay. And we'll talk about that a little bit more later on in this particular PowerPoint, but Newton's third law states for every action, there is an equal and opposite reaction that is occurring. Now understand, Newton's third law can also apply to internal forces, but it might be better understood with external forces. And again, we'll talk about these more detail here in the coming chapters. So with external forces, we can divide external forces into non-contact and contact forces. Non-contact forces mean essentially between the object and the force acting on the object, there is no contact between the two different objects. Okay? So for example, gravity. So if I jump up into the air, okay, the force of gravity from the earth is going to pull me down back to the ground there. So gravity is a non-contact force because force is acting on myself in the air, okay, pulling me back to the ground there. But the earth, when it pulls me back down, is not actually touching me to pull me back down. Contact forces, okay, are going to be between two objects that actually touch and collide with each other. So for example, hitting a baseball there. Okay, so a baseball flies off the bat, okay, due to the external force of the bat hitting the baseball there. Okay, and since the baseball and the bat collide, okay, that would be an example of a contact force occurring between the baseball and the bat. So we've been talking about gravity so far in this unit there. Gravity specifically is going to be the only non-contact force that we're going to be concerned with in this course. Okay? And on Earth, okay, the force of gravity is going to be 9.81 meters per second squared. Again, we're not going to be mainly focused on doing mathematical computations in this course here, but again, it gives you an idea there of how much, or the quantity, or the magnitude of gravity there. Okay. Now, understand that this 9.81 meters per second squared, okay, this is considered an acceleration, okay? So this is an acceleration there, force there that gravity exerts on an object there. Now, this value would change depending on which planet we're on. So if I was on the moon, the force of gravity would be less. So this number would be smaller if we were on the moon. Likewise, the force of gravity if we were on Jupiter, which is a lot more massive than the Earth there, the force of gravity would be a lot higher on Jupiter, okay, bigger than 9.81 meters per second squared. So weight, okay, which we talked about before, is the measure of force of gravity acting on an object. Okay? But the way we can calculate how much somebody weighs there is we multiply an object's mass in kilograms, okay, by the acceleration due to gravity, okay? So this is where that G comes from there. So the acceleration due to gravity, okay, on Earth, which is 9.81 meters per second squared, if you would multiply that by the mass of an object, that would give us our weight, okay? And essentially, this is displaying Newton's second law there, okay? Weight is a force, okay? And force equals mass times acceleration. So weight is actually a force there. And again, in a lot of the literature there, okay, typically weight would be typically measured in newtons there. But people will use pounds, okay, and other things along those lines as well. So we mentioned Newton's third law a little bit earlier. Essentially, this is the law of action and reaction, which means for every action or force, there must have been equal and opposite reaction or force going in the opposite direction. Okay, so essentially, okay, one direction of force is going, and there's going to be a force going in the opposite direction. That's going to be equivalent, okay, to the amount of force going in that one direction. Now, what's important to understand there is that the forces, these equal and opposite forces there, are going to be equal, but the effects of the forces may not be. And we'll talk about that in the next couple of slides. So the reason why these opposite forces may be equal, okay, the effects might not be equal there, okay? And that's due to several things, but two of the more important things is number one, the friction force must be overcome for an acceleration to occur, okay? So for example here, okay, we've got this little kid here, okay, he's trying to push this big sumo wrestler, okay? As the kid is pushing this big sumo wrestler, the sumo wrestler's got a friction force, okay, that is occurring between the ground and the sumo wrestler's feet, okay? So this kid is pushing into this big sumo wrestler, okay, and the sumo wrestler is holding his ground there. So there's an equal force going in the opposite direction, pushing against this kid. So this kid is pushing into the sumo wrestler, but the force of friction is pushing equally in the opposite direction. Number two here, okay, with Newton's third law, the larger the mass of an object, the smaller the effect of force on that object. Okay. So again, this little kid here, okay, is very small. The sumo wrestler is very big there. Okay, so the kid is trying to produce a ton of force to push the sumo wrestler around there. But because the sumo wrestler is so big there, okay, the amount of force that this kid is creating is so small that it's not going to it's not going to see an effect of the force on this sumo wrestler. Now, if the sumo wrestler was very small and was the same size as the kid probably could produce enough force to push the sumo wrestler back. But because the sumo wrestler is so big there, okay, therefore, a lot bigger object, the force of the kid pushing, we're not going to notice it nearly as much. So in review, okay, we had three different terms that we talked about here, okay? Kinesiology, okay, study of human movement, static movements there, okay, either maintaining the same position, okay, or maintaining a constant speed. Dynamic movements means there's some sort of acceleration happening, speeding up, slowing down, or changing directions. Another big term we talked about is inertia. Okay? Essentially, inertia is the object's ability to resist changes in its motion there. So an object at rest will stay at rest, or an object in motion will continue to move unless an outside force acts upon it. We talked about the difference between mass versus weight. Okay? Mass, remember, never changes. Essentially, it's the total amount of matter that makes up an object there. Okay? Mass is a measure of an object's inertia. Okay? Weight is an object's mass times acceleration due to gravity. So essentially, weight is a force. And depending on which planet we're on, okay, weight can change versus masses will always stay the same. Force is going to be mass times acceleration. Okay? If the net force, okay, is anything, okay, anything other than zero there, the object will be accelerating. So if net force is +1, +2, +10, or maybe -1, -2, -10. Okay? There will be some sort of acceleration that is going on. Gravity is going to be the only non-contact force at which we're going to be concerned about in this course here. Our weight, again, is a result of multiplying our mass times acceleration due to gravity. And then we've got Newton's 3 laws. Number 1, law of inertia. Again, we talked about what inertia was previously. Law of acceleration. The sum of the forces equals mass times acceleration. And then law of action-reaction. For every action, there must be an equal and opposite reaction, but the effects of these two opposing forces there might not be equal, though. If you have any questions, please don't hesitate to reach out. Have a good day. Booyah!